Okay, 11:05, let's start then. Good morning, I am Gilberto Thomas from Porto Alegre, Brazil, and today I'm going to present a simple tool from Compass, which is included in Compusel 3D. It is how to build and to use vector fields to help in principle, in visualization of your simulation. I remember you that the workshop is live streamed, recorded, and will be distributed later. And we thank you for the funding from the American agencies listed below in this slide. Let's start. This is the outline of the talk. I don't know if I will use the whole section today because this module is quite simple, but I will try to go slowly that you can learn how to implement those things. At the beginning, I will ask a question about what is a field, what kind of fields we have with some examples, how to represent scalar and vector fields, implementation of these fields in CC3D, and this implementation will be given you through 3 examples that I'm going to use, examples we already built during these previous lectures. Okay. Let's see. Well, why is not going? Ah, here. What is a field? Well, a field, we are talking now fields in the physical sense of field. In physics, it is a concept. It is used to describe a region of the space or the whole space, which presents as you can say a deformation, if you want, created by a physical quantity which is present in it. This space can be measured at any point. Okay? For example, we have here the gravitational field, gravity, magnetism, and heat. All of these three movies are showing something to you, that the objects there are under action of some thing that says so, which is present in the region of the space they are showed. The candle just creates heat, temperature differences around it. The magnetism there make that small cube floats. And the first one, gravity, make the pendulum bounces back and forth. Mm-hmm. So this is our interpretation of a field, like a modification of the space. We can describe fields basically having 2 types. A scalar field, where each point of the space where it's present is described by a single number, just a value, which can be positive, negative, integer, real. Okay, like here you have, for example, the heat from the sun transformed in a map of color map here, a heat map, showing different regions of the Earth, which present different temperatures. We can see these temperatures by colors, but just a number. The temperature is a number. Each region of the map has a different color, which means you have a scale down in the picture that you can see colors associated with temperatures, just a number. Another way to represent this is a vector field. A vector field modifies the space, assigning to each point of the space a vector. I mean, which is a vector. What is a vector? It is a scalar which has associated with it a direction. So this is the example there. We have a Earth in the space around Earth. We have those lines here representing the space around Earth, which shows you how gravity works. If you are near the ground, the curvature of the Earth is so it looks like a flat surface, and the lines behave as they are parallel lane. But you look from outside, from far from the Earth, the lines are represented by radial lines converging to the center of the Earth. Okay, so this is how the vector field works. Now we have many examples. I don't know why it's so examples. There is a specific kind of vector field. For example, the velocity field. It is the velocity field, but it is not the same as the previous ones, because the ones describe the environments, if you want to, and the velocity field describes how the system moves in the space, how it flows in the space. For example, we have here a simple movie showing some clouds moving. We can transform this movement of the clouds in a global wind map, showing how those clouds move in the space, like that. So this is the velocity field of the clouds, the time, the weather, okay? Those are the fields we are going to, we have included as a tool in CompuCell. I don't know why it's taking so long to carry there. See here, for example, we can use velocity field to represent, to map birds like in accelerated time here, motion of a flock of ships, I don't know. You can use vector velocity field to describe how the fluid flows inside a pipe, for example. So, and finally, we can even use velocity field to describe how does the cell move. A bunch of cells, individual cells, a tissue. I see it's very fancy here. See, we can use the velocity field to describe the cell motion. Let's see now how you can implement that. This kind of extra fields, we call these extra fields in CompuCell3D, are included in the package. See, here is a copy of the manual page at the website, the Python script manual in the web page, where it shows you how to implement these extra fields for visualization purposes at the beginning. This is what I'm trying to show you today, how to implement these extra fields as visualization aids for your system. One thing I must say is that these extra fields are not included in the simulation wizard. You cannot find the box to mark it, to include at the beginning in the simulation. We have to do this by hand after the simulation is built. How? Well, to edit in the CC3D Python drop-down menu, there is a tab here called extra fields, where you can include each kind of field you talked about so far, the scalar fields or the vector fields by hand, line by line. I mean, we can describe a cell by its center of mass that we call scalar field cell-based model, or we can describe the cells through all the pixels that the cell has. So this is what we call pixel level, scalar field pixel level. So we have a scalar cell level, scalar pixel level, and also vector cell level and vector pixel level. There is another way to implement this I will show you later in the simulation, which is here down in this drop-down menu here, you add a steppable. You can introduce the extra fields in your simulation by creating a new steppable in in your project, in the steppable file, of course, after you finish the wizard. The steppable file way to introduce extra fields are a way if you want, for example, have more operations, more calculations that will be used to create, to change the fields, the state of the cell, something like that. You can use the steppable. But if you are just using the fields to show some attribute of the cell which is running, which is being defined at the beginning, you don't need to add a steppable. In this way, you only use it to implement it by line by line, as I will show you very soon. So here, well, let's see how I will implement these fields in CC3D. The first exercise, you can download it from the student's materials, the exercise 7.1, or you can do it by yourself using the previous exercise. I did it at the lecture in module 2.3 last week. The exercise where we build a contact inhibition growth. Remember that exercise? We have a bunch of cells growing and multiplying, self-dividing in a square grid, and we plot two graph windows where we watch the growth of the target volume of each cell and the pressure that the cells have during the growth. And we had a function that controlled the pressure inside the cell, as showed here in this slide. The FP equals to K times a function related to a preferred pressure. So I think it's better you to load this 7.1 exercise in the student material. But if you this first one exercise telling you what to do, okay? So you load if you have that exercise, you load that exercise and save it with a new name. For example, 7.1, just to not mess with the existing exercise. So when you do that, all the files you have inside the exercise 2333 is going to be saved as a new project E7.1. Then let's go to the code. Let's see how it works. Here, when you open the exercise, you go to the steppable file, go to add steppable, and a secondary window will open, a pop-up window will open, where you define the name of the steppable and what kind of implementation field you want to include. Here, I marked, I called extra field visual steppable something. You can name it whatever you want. And I chose to be a Scalar cell level field. Click OK. And immediately, the first thing it has is the intermediate file, the Python file, the main Python file, will have included the code of that for that stable I just created automatically. You don't need to worry about. See, here it is the line in the main Python file. The stable I just created, extra field visual stable. And the frequency it's called, you could define here in the definition of the stable, it's 1 here. Oh, now what happens in the steppable file? In the steppable file, it is open series of lines with some, in each part of the steppable, you are going to define the name of your cell name you want. Okay. Then the other lines are the start function as usual. You can put something here if you want, some initialization variables, parameters. And in the step function, you are going to edit to include what your field, your Scalar field, how it's going to be. I mean, you have to fill the vector, the space, with some quantities, the numbers, remember? How you do that? Well, let's now to include the extra fields, the lines which we define as Scalar. In the first part here, you choose, you have four lines. One is an example. If you have difficulty, you can see the example. And in the first line, we include here the initial, the line in the init part, which has already been included by steppable tool, the wizard tool. And now we are going to include the part where we want to fill the field with values. I'll do that this way. We did the code. This is the way you have to implement. I'm creating this field here, two Scalar fields. One to show the pressure, one to show the volume of the cells in that old exercise we had. So I created two Scalar fields here, self-scalar P, self-scalar V for pressure and volume, and they gave it a name, pressure and volume. In the start function, there is nothing to include in here, only in the init part. And in the step function, I have to do this to fill the field with values. First, I create two placeholders, field P and field V, which are the place where I want to put this scalar fields. Scalar field P, self-scalar field V. And then I will fill the fields, these placeholders, with the values we want. So remember, in the exercise, the pressure was a dictionary for the cells, included as a dictionary. So in the field P cell, I will do a loop over the cells, and for each cell, I will put the value of the pressure of that cell. So I'm saying that in the position of the cell, the value is the pressure of that cell. So this is the spatial value of the cell, the field. And the position of the cell for the other field, I will put the volume of the cell. Let's see if I can here use the text to open my project here. Exercise 7.1. This one. So slow, my computer today. Here. Let's see. Here is the stepable. See? I can close this one, can close this one, and close this one. Here is the steppables, exactly as it is there. So we have now both fields, pressure and volume, filled with the values at each point of the space where the cell is. Let's see how it works now. See? Let's start over just to see. So the code is already, the setup for the windows are already prepared to you. But when you open for the first time after you include those lines, you have to add two windows here, two new graphics windows, one for volume and one for pressure. And that's it. I don't have to include in the simulation any plot, graphical plot to plot the fields. This is automatic. I need to open the windows to show the both fields. Okay. So when you put to run here, you have the cells growing and multiplied. That there's two graphic windows you already know from the old exercise, for the previous exercise. And here you have in a color map the volume and the pressure of the system of each cell. I stop the simulation, I pause the simulation to show you. There is a color code, a color bar here, saying relating the volume of the cell with the color it has in the simulation. So the red, the head cells are big and the green cells are smaller. We don't have the smaller one because our cells always started with 25 grid points. So the minimum color here is the green zone. And after that, there's some cells growing, and almost at the division point, they are red. The same is here in the pressure window, we can see the pressure is also in a color code here. See here, we have negative pressure. The cells are growing, and high positive pressure, the red ones. You can compare, for example, those two graphs. As you can see, this relate the volume of the cell with the temperature, with the pressure of the cell, comparing, for example, this orange cell here at the top with this green here in the top. So it's the same cell. Here, the cell is almost get to the point of division, and here the pressure is not too big. So you can map everything. If you continue, remember I had included the steppable through the wizard using the add steppable from here. See, I built it from here, gave it a name, to let the frequency of calling 1, and I chose scalar fields. Okay, so this is what happens. The Python code, the main Python file has a line automatically included by the wizard, which is the call for this new steppable. And at the steppable part, we have a bunch of lines that we have to edit. For example, I will back to this slide, maybe the previous one, to show how this part here is how it is the left window, how the steppable is included in the file. Okay, this extra field visual steppable here, that one that include. So after editing, those are the lines I have. And then I have here the editor. So I created two scalar fields for pressure and volume. And this is the way we fill the field with the values they should present. So we define here two variables, which are placeholders for the field, like a function with points. And I say that I make a loop in the cell list, and I say that the field pressure of the cell of the list is the pressure of that cell. And the field volume for the cell in the list is the volume of that cell. So I'm doing a map here in the grid, saying that in the position of the cell, the pressure is the pressure of that cell. The same to the volume. At the position of the cell, the value of the field volume is the cell volume. Okay, I think we can catch this. So putting it to run, again, here, we have this. Let me stop here. Let me say again what I have said before and you didn't hear. When you run the simulation for the first time, the only windows that will appear are the old ones, the cell field and the plot windows, the graphical windows. To see the fields, you have to go here and open two new windows. These two new, each one you will choose for either volume or pressure. Okay, then I have two windows, volume and pressure window. When I put it to run, wow, why it's that? See, the graphical windows show you the thing you already know from the previous exercise, the old exercise. But in the field windows, you can see how, let me stop here to analyze the graphs, the windows. For example, this window, volume window, what I was going to say to you, we have a color bar here, which relates the size, the volume of the cells with a color in the simulation. So, for example, you have red header cells, which are the bigger ones, just about to divide, and the green ones, which is just divided. Remember, we don't have any one color below 25 because our cells have a minimum of 25 grid points. So this goes from green to red. The same thing, same kind of behavior we have here in the pressure. We have also a color code, and the pressure can have any value if the cell are under pressure or exerting pressure. It can be negative or positive. So the more red cells means bigger pressure. So let's run to see the region. The cells occupy all the region of the lattice, and you're going to see there is a plateau being achieved by both situations. The target volume reaches a plateau, and the average cell pressure also goes to a plateau. And this way you have to, for example, if you look at the graph here, the average target volume for the cells is about 36 grid points, like that, 35, something like that. You see here, which have an average between these values about, I don't know, maybe it's bluish. Oh, yes. Now we have a question here. Because the cells are a little bit smaller than the average size. Actually, 25 is the average size. So we have a bigger distribution of cell size here because the cells start to divide just or divided just after the space is completely full, so they don't have time to grow to the size of division. So you have a bigger distribution of cell size here, which is showed you about with the number of colors in the window. Here the pressure also has a more green number of colors here because the cells are average around that value of 70, something like that, which is the green part here. 6770. Oops, what is that? Okay. Okay, so this is how the scalar field works. So you just need the color. Okay. Now, we have, so in summary, we have both scalar fields here. Okay. We have the placeholders for the values here. And the filling of the placeholders with the values of we want to see, to watch during the simulation. So this is the simulation. So I had showed you, I got a little bit lost because of the glitch in network. And one thing I forgot to say, in the simulation window, we can adjust a lot of things about these fields in the CC3D preference. You let me show you, where is that thing? Oh, I know what I did. I just closed the drive. So I lost my Google Drive. Okay, there I have. So let's open here the player again. Pause here in the tools, configuration, fields. See, we can choose which field you are going to configure here. If you want to show axis, something like that, around the window of the plot. You can choose the size of the scale here, minimum 0, fixed length, if you have, well, no, you don't have vector now. If you choose, if you want to put legends, how many legends? So say it has a kind of configuration the way you see that window. You try. There is also a possibility to put scalar contours, which is not the case right now, but anyway, it has this to that. No, this is okay. Now, continuing, let's see. What's going on? Jesus. Sorry, guys, today is kind of complicated here. I don't know what's going on. Let's start over here. I think with the loss of this time, the internet, that time I have to reopen the file. Sorry, just a second, please. Okay, now I have it again. Oh, sorry, now I passed. Okay, so that is the simulation, how the simulation ends. You can track that thing here. So let's go next, move on, and see how we implement now a vector field. Remember, the vector field is the field which is described but not only a single number, but also with a direction in the space. I mean, each point in the space is described by a vector. And we are going to show this in that simulation that Julio has showed you yesterday with that bunch of cells, the mitotic cells, compartmental cells in the movie. So we are going to assign to each cell a vector. Sorry, I have a cat problem here. Just a minute. I'm gonna. Well, okay, sorry. We are going to describe, try to describe the motion of those cells with the velocity field. So now we are going to use the other example that you can also use the Julius example to edit by yourself, or you download from the student's material the file e7.72.zip. So let's come here. I'll close this one, discard, and open exercise 7.2 here. I'll close this one. Okay, let's see from here to begin. Okay, again, we are going to make a small modifications in Julius code, which is really my code that I used last week as well. He took that code, it adapted to compartmental cells, and we are going to change some things here to make it faster. In this cell lambda volume for the nucleus compartment, we are going to put 4 instead of the original 5 it has there. And in the number of cell divisions, I will limit the cell division to the number of 16. I mean 8, because I do not want to fill the grid with too many cells, that because it's gonna to be complicated to watch the cell vectors at the beginning. So I included this line here. That this line say that if the amount of cells that I have is smaller than 16, I will continue with the division. If the number reaches to 16, it stops the divide. Okay? And also I increase a little bit the probability of division to 0.01 to 0.05 here to faster the things. Okay? So the implementation of the steppable is the same as before. We open the CompuCell drop-down, the 2-digit drop-down menu from here, add steppable, and now instead to choose the scalar field, I choose a vector field, and then give it a name. The name I have done, the choosing is extra vector visual steppable, like that. So remember, we are going to map velocity, and to have velocity, I have to calculate velocity for the each cell. So we are going to proceed in that way. To calculate velocity, we need the position of the cell at 2 different times. Then we calculate the displacement and divide the displacement by the amount of the time that has been occurred from the first position to the second position. The very easy way we have done this before. So this is what I have done here. Okay, let's see here how it we enter two dictionaries. We have two new dictionary entries for the position of the center of mass of the nucleus here. We include this algorithm here to calculate the speed, the velocity, the components of velocity. We define the placeholder for the vector field at this line by showed by the red arrow here. And finally, we fill the field with the components of the velocity. See, let's see in the code there. I think it's better to see it because here I can, let me stretch this one. See, then here is the two lines to store a previous position for the center of mass. Here I define the interval of time that I'm going to use to calculate the velocity components. Here is the implementation of this vector field, the placeholder field. And here the algorithm to calculate the components of the velocity. Remember, we have also to include that part where we have to test if the cell had crossed the boundaries, the x boundary or the y boundary, and correct to have the right amount here. So then we calculate the components this way. Nucleus velocity x is del x over time interval, and the nucleus velocity y is del y by time interval. And we fill our field saying that the field at the point where the cell is has a vector with two components, in val x and in val y. So here, see the difference from the scalar field. The scalar field is it was only one number, the pressure or the volume. Yeah. Now we have two components because we are assigned a vector at that point of the space. And finally, we update the dictionary to retain the actual position of the center of the mass to be used in the next time I will calculate the velocity. Okay. Okay, let's go to the simulation open in the player. It's so strange, this behavior. See here, let me stop here. Here's the cell, which has wrong colors here. I will not lose time about them. No, okay, let's change the colors. I don't know, the colors here are right and there are wrong. I don't know why. Anyway, it's a CompuCell player bug right now. And here is the vector describing the nucleus velocity of that cell. Okay? It's an arrow, like a cone or a triangle, and you can adjust the size of this arrow here. See, length of the arrow. I can, for example, let's try 10 just to look at it. See, it increased the size. And when I put to run, of course, here you don't have too much. Also, the color is associated with the magnitude of this vector. So this and the orientation, the arrow, the point of the arrow is the direction where the cell is moving. Of course, see the cell divided, you have two arrows. At this time lapse, you cannot see much thing because the simulation is so slow and the images are being created at each 100 Monte Carlo step. No, the calculations are being made at 100 Monte Carlo step, you don't see much. But if you store these images and then make a movie, as Julio did yesterday with the cells crawling around and then multiply it and then changing directions, that is a movie made with some images from the simulation, and then you can see things happen more properly. Okay. I also see the probability of division is small, so the mitosis occurs kind of slowly. It's a random stuff, but every time we have a division there, you have a new error in the graphic fields, graphic windows, and is showing what the direction are the cells moving. This exercise is just to show you how to put the arrows in a window and see the connection between the motion of the cell with the orientation of the arrows, and the colors with the intensity of the velocity. Good. So this is the final. I let the simulation goes for a longer time, and I have a bunch of maybe the 16, 15 cells already shown in this window here. Now, finally, I include two fields, one of each, one a scalar and a vector field. And I will use those fields in that flowing cells that I showed last week as before. So we have, remember, we have that cells coming from the left. There is a source of cells just around the border. The cells flow to the right, entering the channel, and faces around obstacles, and after the obstacles there is a sink where the cells disappear. Okay, again, you can use the exercise 4 to do it by yourself, or you can download the exercise 7.3 of the student's material and do and follow the explanation directly from the bread simulation. So let's see now how I implement that in the file. Projects, open, exercise 7.3. Here. Yeah. Okay. This way I'm not going to use this add steppable tool. Okay, I will do the different way. I will put line by line. So if I want to put line by line, see, the first thing is I have to include, again, I'm working with velocity, I need the position of the cell at 2 different times. So I have to create a new entries in the dictionary, as I did in the previous exercise. This is here. Okay. But there is another thing I have to include now. As remember, we in this simulation, we have cells being created at the left end of the grid, in the source part of the grid. And every time I create a new cell, I have to give to this new cell the attributes that should have. So here I give to the cell the target volume, the lambda volume, the force which is acting over it, and I have to store the initial cell positions. I have to add the entry to the new cell dictionary to store the actual position of this, which is in the XY position that I'm creating this new cell. Okay, so those lines for the dictionary for the cells which start in the simulation, and these new entries here for the cells that are being created during the simulation. I cannot forget that, because otherwise the new cells won't be traceable in time. Right? And here is the part where I include the fields. As usual, in this init part of the class, the channel steppable, I include the two fields. One vector, one scalar. The pressure for the scalar, the velocity for the vector field. And here I update the velocity and fill the fields with the values they must have. So here I create the placeholders for the scalar and vector fields, field V, field S. Okay. Here I included that algorithm, the algorithm for velocity calculations from here to here as the previous one exercise. And here I filled the fields with the values we need and update the dictionary positions. Okay. Doing this step by step here to be just to the presentation you have all of this that I just said, written one by one, saying that show you how to include the lines, updating the fields here. See, field, algorithm, and filling the fields. And now let's see the simulation. I have to stop this one. The simulation running. This is quite interesting. Open player. See? Again, the window that comes to you is the old one, just the cell field. And you have to open two extra windows here to show the velocity field and the pressure field. Okay. So let's move. I think I should decrease the size of the arrows, because now the configuration file has size of 10, I think, yes. It's too big for the simulation. Well, not change. See, this left window is the old simulation we saw last week, with the cells going to the channel. And there you have the, why it's so big that, let's see if it changed. Yes, it changed. Let's just put a little bit smaller, just to, see, you can see the cells change direction to enter in the channel. The speed increase a little bit inside the channel. Again, if you do a movie of that, it's going to be much more beautiful to see. Here you have this glitches, this stop and go, stop and go, stop and go. It's and you have to wait a little bit to the cell reach the cells reach to the obstacle, just to see the arrows make the contour in the obstacle. It's just about that. At the same time, you can see at the left end here, cells are being created with big pressure here, see? And there is a color code here showing how the cells, how the cell pressure behaves outside, near the source, inside the channel, and near the obstacle. See? Okay. Well, you guys have the code, you can play with it if you want. Go here, continue here. This is the final image for the simulation. And so this is the way you can use, I mean, one of the ways you can use the fields, extra fields in CC3D. And there is another, more ways to use extra fields. For example, you can use reaction diffusion equation to create some pattern in some place and modify the space according with some diffusion and make the cells behave according with the space with a chemical field that is there. So you can use chemical fields to orientate the cell movement through some external source. And there are many possibilities. Maybe Pedro will show you in these lectures with cell migration, compartmental cell migrations, the details in his next lecture. I think it's tomorrow, I don't remember. So that's it for today.
Hello guys, so my name is Pedro. If you don't know me yet, I've seen many people from last week in the chat. I hope you all are enjoying the second week. And I'm about to show you another useful way of using vector fields in your simulation, but not just as a visualization. So Gilberto was showing, yes, we have in 15 minutes, we will have a break, Ghostman. Yes, I will take 10 to 15 minutes now. So Gilberto was teaching you how to use vector fields to visualize fields in your simulation. So for example, vectors in your simulation. So for example, if you have cell polarization in your simulation, you can use the vector fields to visualize the polarization. Or if cells are moving, you can visualize cell velocity. Or if cells, for example, I don't know, are pointing towards some direction, you can visualize this direction. But I'm about to show how you would use vector fields to model something. So the vector field would be part of your model rather than just a visualization tool. So for example, this slide could be my entire talk, because this is a challenge. This could be a challenge for you. So how would you model a bunch of cells in a swirl? Okay, so they are all dancing around each other, around a single point in space. And this type of behavior, it's not so trivial to model. Actually, for example, with compartmental cell migration, you can achieve this behavior. With alignment, you can achieve this behavior. But let's say cells are moving this way not because of, for example, interaction between neighboring cells. They're doing this. They're behaving like this because the matrix, the external matrix, are oriented this way. So let's say the matrix are connected in itself, forming a circle, and the proteins in the matrix are oriented. So if this was the case, well, you would need another type of modeling. Okay, so would you be able to model this behavior using diffusive fields and chemotaxis? Yes or no? Could you? Is it possible? Only using vector fields, only using diffusive fields and chemotaxis. Is it possible to model this behavior? Question mark? Why not, Julio? Yes, Shlai. Why not, Julio? Can I build a chemical field only if the field has a nice expression? Yeah, so Darshan, get to the point. So we only would be able to model this if we change the field in time. So all cells, yes, yes, but Shalai, there's a problem there. I was talking about the diffusive field, so it's a scalar field. You cannot measure the curl of a scalar field. Yes, exactly. So with a scalar field, so yeah, the best answer is Shalai's answer. So this is a field with a curl. So you cannot have a curl of a scalar field. Yes, you would have you need a vector field with a curl. So this vector field cannot be the gradient of a potential, as James is saying. Yeah, and there are some experiments showing cells in a swirl like this, but they are in a confined space. They have polarization. It's a different type of system. But in this case, particularly, you could be, for example, modeling. Yeah, so let me just show you the answer here. So with vector fields, with a curl above 0 in 0, you can model this type of behavior. So for example, the cells are sensing the orientation of the lattice and they move accordingly. So some applications in biology, you could be modeling orientation of fibers in the ECM, the internal cellular fibers as well. So you can set these vector fields for each cell. And inside a cell, for each pixel of the cell, you could set a different fiber orientation. So it's very powerful. Inside a cell, you can, for different pixels of the cell, you could assign a fiber orientation there. And for electric fields is also possible to model. So let's say, for example, in the case of Julio will build a very interesting model of foams in metals. So he has access to particle accelerator. He uses ions to produce hot patches in a metal, and it creates bubbles. So what if he applies a electric field in this metal while he is bombarding this metal with ions? What type of structure could he get, right? So he could use electric fields or magnetic fields, and he would model it as vector fields rather than chemical scalar fields, right? So to build a happy kernel of cells, we don't have time. We only have like 10 to 15 minutes. I'm not sure we have time, but the simulation is very simple. Basically, what you would want to do is create a small lattice, a few cells, contact, volume, and external potential. Okay, I hope everyone is familiar with these three from last week. Then set external potential to be center of mass based. This is not extremely important to the model to work, but this is a nice tip I give for you. Use center of mass rather than pixel based. Create a rotational vector field in the middle of the lattice. So I have two tips. The first one is use polar coordinates instead of Cartesian coordinates, because it's much easier to build a circular structure, especially in a vector field situation, and make the vector a unit vector. So in this case here, this specific vector field is not a unit vector. All vectors would have the same size, but in the simulation, I am using a unit vector because otherwise the cells, for example, in the outside cells would travel much quicker than the inner cells, which is not a problem, but they can die because of the excessive force. And you have to update each Monte Carlo step. You have to loop over all cells in the simulation and update the external potential attributes, the lambda vector x and y, based on the direction of the vector field in the cell center of mass. So that's all you need to build this model. I will show you the code for you guys to see what it looks like. So are you seeing the code or not? Yeah, okay. So I have here the external potential. I have to track the center of mass as well. Center of mass has to be loaded. It is loaded by default, so don't worry. The volume and the contact energy. So these are all I have. So I don't have any diffusive fields, okay, which makes the simulation run faster. And the uniform initializer, just creating a few cells in the middle of the lattice, and that's it. Yeah, I will send a demo to you real quick. So let me here. Compress and in Drive. Where is it? Shared with me. Student materials, demo code, and I'll create a, I think, module 9.1, I think, but I will specify because I'm not sure. So no, I'll call it model vector field, because I'm not sure about the order of the lectures. So there we go. The demo is uploaded, and let's go back to the code. Okay, so this is all I have in the XML, and in the Python, I have set two forces. So a chemical force, this Q is actually referring to the vector field, and this F is an intrinsic force applying on cells. So my cells without, let me just show you, without the chemical force, they can move randomly, which I will show you. Open here. So they can move randomly in my simulation, but I was demonstrating without the intrinsic force. Takes a while to open. Yeah, so they can migrate intrinsically because they have this force, this random force. And there is an angle that I set, the angle changes uniformly. So the cells have, I don't know why this cell stopped. This cell just stopped for some reason. This is very strange, but okay. Ah, I know why, but now I know. Yeah, I know why. Yeah. Yes, and I have to fix this. But yeah, for now, let's not worry about this bug. So with the vector field, you can see that now they don't have any intrinsic movement. They just follow the vector field. And to show you guys the vector field I have is basically this circular arrows here. Yes, so I have a division by 0, Darshan. And when you have this type of problem, like a division by 0 in the force, cells freeze. Cells freeze. Yeah. So the problem is right here. I am dividing by R, dividing things by R here. And when R is 0, which means I am exactly in the center of the lattice, R is 0. And if a cell crosses the center of the lattice, it will freeze, which that was what happened actually. So that cell was unlucky, and it crossed exactly in the center of the field. So to prevent this, you can, for example, one way to solve is to sum small quantity in the R, and that would work. Yeah. Yeah, that's it. So let me show you how I did this. So first, this is the creation of the vector field. You have to import like self-create vector field, you give it a name, and you initialize in the init function. and you pass it to a self variable, a class variable. So it has to have this self dot and then the name of the variable. And then here I am looping over all pixels in a simulation. So for X, Y, and Z in self every pixel, these are all pixels in the simulation. And then here I am transforming X and Y to polar coordinates. So R is a distance, and as I want the distance from the center of the lattice, the center of my lattice is the pixel 50, 50, X 50 and Y 50, because my lattice is 100 by 100. So 100 here, 100 here. The center is 50, 50. All right. So this is a distance. So the square root of x squared plus y squared, this is the distance. And when you do the minus position, you are recentering your coordinate to that point, specific point. So my specific point is 50, 50. So I just do minus 50 in the x, minus 50 in the y. So I recenter my my vector field. If I did like 20, I have to do in everything. Okay, I am recentering here, so you will see that my vector field is recentered to 2020 now. So the 0 is right here, and my cells will follow another path. Let me show you the cells and run. Yeah, so now they are following another path. Yeah, and there's a bug here, which I have to fix later. So let's go back to 50. So here I'm building my polar coordinates. So R, the square root of distance. Actually, sorry, R is basically the distance to the center. So this is the distance to the center. And then the angle. So I am calculating the sine of the angle, which is y over r, and the cosine, which is x over r. Okay, so some basic geometry here. So if you have a triangle, a rectangular triangle, the sine is the opposing side of the triangle relative to the angle, divided by the largest side of the triangle. So the largest side of the triangle is r, and the opposing side of the triangle is y, and x is the like the adjacent side of the triangle relative to the angle, divided by the largest side of the triangle. So this would be the cosine. So this is sine and cosine. And to build my rotational vector field, I just have to, for example, I have to come up with the rule to create that swirl. So for example, in the x coordinate, I have to write r times sine, and in the y coordinate minus r times cosine. So yeah, this is not easy to explain in a few minutes, but you can type whatever you want actually. So if I invert this sine here and cosine here, I will get a entirely different shape. Let me show you. Yeah, so this is a completely different shape. You can see that in the y-axis and in the x-axis, we have the vectors pointing either inwards or outwards. So this will generate a strange behavior for cells. Yes. And when they reach the boundaries, they crash for some reason. But yes, so you can see that in the y coordinates, arrows are pointing inwards and cells are following that direction. So they are not following the direction of the lines because my lambda in the external potential is negative. So I only have to, oh, actually it's positive. It's the opposite of what I was talking about. And then after generating the vector field, I just have to parse it as a force. So this is the force. I actually don't need this term here. So this is the force, basically is a constant times the direction of the vector field, which is self.vf. Vf is my vector field. And the coordinates of the cell, which x and y, you can see here, x and y are the coordinates of the cell center of mass. And the zero component is the x component, which I'm parsing to the lambda vec x. And the y component is being parsed to the y component of the external potential. Okay, so this is not needed. This is not needed. Just to be simple for you guys, this is not needed, and this is not needed. Right there. So if you want to build a simulation, you can take a look at my screen here and build it yourself. Or just download the demo from the drive and play with it. So you can set different vector fields. So for example, a simple one would be, let me build a possible vector field here. 1 in the x, 0 in the y, and 0 in the z. So this could represent, for example, an external scalar matrix with orientation in the x direction. This simple here. So x direction orientation. Very simple, right? You could, for example, orient it towards the y direction. How would you do it? The letter Q is the strength of the force acting over the cell. So if you see these two lines over here, so the Q is modulating the force strength over the cell. So it's multiplying the direction of the vector field. Yeah, that's it. Yeah, it's not the magnitude of the vector field. The magnitude of the vector field is 1 in my case, because I'm dividing by r, so the magnitude is 1. But when I parse it to the cell amplifies the value of the vector field as a force over its center of mass. Question for you, Shalai. I am building a ECM with fibers orientation in the y direction, pointing upwards. How would I write this line over here? This 20th line, how would I write it? Darshan was fast. 0, 1, 0. Perfect. That's it. So you would write something like, instead of this, I would write 0, 1, 0. Yep, that's right. So let's say you want in the diagonal, positive x and positive y in the diagonal, like so. In your case, like this, pointing to this direction. How would you write the vector field? Uniform. Now normalize it, Darshan. Make it a unit vector. Perfect. That's it. Yeah. So you would write precisely what Darshan is putting in the chat. So you basically will divide by the square root of 2 like this. Yeah, perfect. So this in the diagonal. Perfect. Now let's say you want to build a matrix like let's see. Let me draw in paint. So I have a region. Where is it? Okay. So I have a region here. I have my cells crawling randomly inside this region. But here, specifically here, I have fibers pointing in a direction and only in this particular place. So the fibers are located in this square. How would you code it? How would you implement this region? Let's simplify. It's too hard. Just one fiber in a given direction, just one fiber. How would you do it? Define a piecewise function for the boundary. Oh, I got what you mean. Yeah, so basically, yes, what Schley is trying to tell us is that she would probably create an if statement, or Darshan, yeah, Darshan is doing the other way. So Schley is building the field, and Darshan is conditioning the cell response to the field based on the position of the cell. So these are two different approaches. Yeah. So Schley is building the field. So in these limits, I set the field inside, and Darshan is saying, if the cell is inside this region, the cell responds to the field. Yeah. So these two approaches will lead to the same result, but they have different interpretations. All right. So just to build just one line, what I would advise is to parameterize the arrow, this particular line, using the vector parameterization method, and then you can assign for each point of this vector of this line, you can assign the vector direction. So you don't need to loop over all cell pixels doing this. If you parameterize this specific line, you don't need to loop over all pixels. It's much easier. And then you can, for example, model fibers in your simulation, like a single fiber in your simulation using vector fields. All right. So if you want to do this in your simulation, like a single fiber somewhere in a given location, I can help you with. Okay. So don't worry if you're not familiar with this analytical geometry mathematics that we are talking about, but you still want to implement it in your model, feel free to call us to ask us for help. So you don't need to have the domain of these concepts to build your models. You can simply call us for help, and we will definitely help you with this part. So some people will struggle with biology, knowing mathematics. Some people will know the opposite, will know biology, struggling with mathematics. And that's why we work in groups, right? So in hackathon, especially, we encourage people from different backgrounds to work together to try and solve the largest number of problems that could appear during the development of the model. So that's it from my part. I hope you got a sense of how you could use vector fields in your simulations as part of your model, not only to visualize something. Okay, so this is an example. This is a very funny example. I don't see an application of this particular simulation here, but I want you to get a sense of what you could do with it. Please fill out the questionnaire. I know there wasn't enough time to build the exercise, so please vote. There wasn't enough time. This is part of the process. So I would agree there's not enough time, but I appreciate your attention. I hope you learned something new about vector fields and how you could use in your model.
Good morning, everyone. Thank you very much for the opportunity. I talked about projects on working on 3D retinal pigment epitheliums during the hackathon pitch. So I just want to get some insights on it. Okay. I want to share my screen, please.
Oh, yeah. Let me stop mine. Can you share your screen, or I can maybe give you the permission?
Screen share should be okay. Try it.
Okay.
Ask to allow. No. Can you share your screen?
Okay, let me try it now. So, can you all see my screen, please?
Yeah.
Okay, so this is the 3D model we've been working on. The initial part of it was I got help from Dr. James Luca. So then I was able to reduce it to this form. However, this isn't the structure we want for the basal surface. The basal surface follows the hexagonal shape, which from the apical and the lateral. However, we want some irregularities. We want an irregular surface area, which I showed it during the hackathon. I can share it also from here. So, hold on, please. So this is the exact basal surface we're trying to reproduce. Can you see this, please? Hello?
Yes, we can see.
Okay, so this is the exact one we're trying to reproduce. This under figure A, the last image, we want it to produce irregular structures at the edges, exactly the way we have it here. So I tried introducing noise into the CompuCell Python code for just the Pesa surface, and however, it isn't working for the structure. It's actually not giving me the structure I wanted. And also, I followed Professor Glazier's. Well, he gave me an advice the last time about introducing some kind of chemo attractants. I saw a paper on it and I read it, but I'm unable to implement it. So I just need some help with this.
I think it's important to understand what is the mechanism behind these fingers that the cell protrude into space, because the difficult part is the basal cells, right?
Yes.
So the mechanism behind these protrusions is what will define the way you model them. So, for example, if they happen only by, for example, only by adhesion, or if they happen because you have actin fibers pushing the membrane, these are two completely different modeling schemes.
I do understand that. There was a paper I read, it's a final year, a PhD thesis. I read a PhD thesis which talked about the adhesion property for the basal surface. I tried relaxing the adhesion property, and yet I'm still not getting the exact image here. Because from the paper I read, the PhD thesis talked about the cell-to-cell adhesion. Then I discovered that whenever I do that on my code, only the interaction between the cells, I only see the changes between the interactions, not at the edges itself.
I'll try to get this shape now with a single cell. Okay.
Okay.
I'll try to build a simulation and achieve this strange shape. So give me a minute.
I did some tests. If you simply increase the surface area, it doesn't work. It just fragments the cells. I think what we might have to do is that lower layer cell might have to be a compartment cell all by itself. It's made up of maybe a core and then these extending bodies.
So to get, I mean, this is probably something we should, I mean, it's good to have it brought up with the whole community for ideas, but this is the kind of thing we can brainstorm in the next session. I think that this is, to get interdigitation of this kind, you're going to have either a curvature rule, which CompuCell doesn't have as a built-in, so you'd have to write an additional plugin for it. Or you're going to have a chemical field like the one that occurs in angiogenesis, which leads to a surface instability. Or you're going to have to do what Jim says, which is to put in compartments into the cell and have those compartments then generate the structure. And I think we talked about this before. You need to look at the existing mathematical models, and Sharon Lumpkin at for example, North Carolina State has built models of this kind about how you get fingering and interdigitation in cell structures. And then you're going to have to think about how to build that. You could do this with reaction diffusion equations, for example. but we'd have to look at which reaction diffusion equation to use. Just looking at contact energy by itself or surface area by itself won't do it, because if you imagine let's think about this. There's something very fundamental here, and I know we want to get back to our next module, but it's of interest to everybody, which is one of the things in CompuCell is that to begin with, a cell is a blob. All voxels on the surface of that cell are identical. They all behave identically. If I look at my interdigitation, I have regions which are coming out and regions which are coming in. There has to be some reason that those two regions are different from each other. And so unless there is something else which breaks the symmetry between different points on the surface of the cell, you cannot get that kind of interdigitated pattern. And so by itself, contact energy can't do it. Now, if Giulio talks about delta notch patterning and reorganization of molecules on the cell surface, that can do it. So, for example, the PIP2, PIP3 reorganization mechanism, this isn't PIP2, PIP3, but an equivalent of that could do it. A lateral inhibition Turing type mechanism where there are regions of the surface that have something that causes protrusion, and they inhibit protrusion in neighboring regions. So short range activation, long range inhibition could also do it. But you are going to have to decide which of those mechanisms that you're going to use. If you want it to work with many cells, then whatever that mechanism is has to operate only inside the cell. Can't operate outside the cell because it'll conflict between cells. And so if you're going to do a reaction diffusion mechanism, the chemical field that each cell responds to has to be confined to the cell. That makes it a little more complicated in CompuCell. So there are a bunch of issues here that are quite interesting, all of which I think are soluble, but are which could be somewhat challenging. And so we'd have to think about the best way to do it in these particular cases. Again, coming back to this, ultimately, Pedro asked exactly the right question, which is, what is it about the cells that is causing interdigitation? Is it particular regions of the membrane have particular molecules on their surface that promote particular curvatures? Is it that there are particular receptors on those surfaces that cause them to protrude into the neighboring cell in a delta notch type mechanism? Is it that there is a particular architecture of the cytoskeleton? These are all questions that have to be asked.
Okay. Okay.
So let's continue that discussion. This is exactly the kind of discussion we want to have in the next module. So it's a great introduction. So